3, 2, 1. Final
Final
project.
project.
Okay, that was great. That was a good take. Let's go.
To begin, a brief overview of projectile motion. A projectile is an object on which the only force acting is gravity. This means that the projectile experiences acceleration downward or in the vertical dimension. A projectile also has motion horizontally, which is uniform or constant. And the mass of a projectile has no effect on the speed of a projectile because the speed stays the same and does not increase. So it doesn't really matter. And then a little bit about kinetic energy. The formula for kinetic energy is mv squared, and it really tells us everything we need to know about kinetic energy. With m being the mass or an object, and v being the speed, which represents motion. So, really, kinetic energy is the energy in motion. Kinetic energy is or follows conservation of energy by being converted from or to potential energy. Um, Kinetic energy, as we can also see once again from the, is proportional to the speed squared. Based on those that information, we came up with a hypothesis about the energy supplied to a projectile and how that affects the velocity of the projectile. So, since there's no horizontal acceleration, the all of the projectile's horizontal velocity must come from initially supplied kinetic energy, right? So, we want to find out we want to measure if the kinetic energy will behave as we expect it to, which is that if we increase it by the same amount each time, then the velocity of the projectile should also increase by the same amount each time because they are proportional to each other. And we also wondered if that information would be useful to find if a bunch of cannons lined up against each other would be enough to break glass.
When we say cannon, we don't mean your normal kind of cannon. We have our pride and joy, really, our son. This is the magnetic
Our
cannon.
baby.
You might have a few questions like, what is it? How does it work? And those are really awesome questions. Thanks for asking them. We're going to answer them. So, we're going to go through basically the physics of what's happening in this cannon. It's set up so that the trigger, which is down where that helpful red circle is empty. And there's two steel bearings in each compartment, as well as at the end where a bearing will be fired from. In order to fire the cannon, you place a bearing in the trigger slot at the bottom with the red circle. This bearing will accelerate towards the first magnet, and its forward momentum will be transferred through that magnet, through the first bearing, and into the second bearing. There are two bearings in each compartment, so that the second bearing's magnetic attraction to the magnet behind it will be weak enough for the transferred energy to send the bearing forward. Once this bearing moves forward, it's close enough to the next magnet that it's going to feel the magnetic attraction from that and accelerate towards it, adding even more acceleration, more speed into this bearing. So now this bearing is going to hit the next magnet, and more energy is transferred into it. And then this continues until you reach the end, and the momentum is eventually transferred into that last bearing, and it's shot off into the distance.
So
Okay.
ultimately, the cannon amplifies the speed of the projectile um, over multiple different configurations, which involve the number of magnetic slots that are filled with bearings. We used this cannon for our experiment. Do you want to go over the experiment?
Yes. So yeah, as you mentioned, you can have four different like configurations so that you can have different amounts of collisions happening and momentum being transferred. So we decided to use this to figure out of curiosity, like how much the velocity would change with each different configuration. The materials we need are the cannon, 9 steel bearings, which are 1 centimeter, if you were wondering. I don't know. A popsicle stick, which you have to use to reset the cannon. Fun fact, behind the scenes. Also, measuring tape. Um, but like the clothing kind that you can lay flat and it's not all metal. As well as scotch tape and a phone to be able to record the times. To set up the experiment, we put the cannon into the 4-section configuration first, and then we placed it on the edge of a table. We used Scotch tape just to mark where it was so that we'd know for the next trials and be able to put it in the same place. We also taped measuring tape onto the floor, starting directly below where the bearing will be fired from the cannon and then extending outwards in a straight line. During the experiment, we had one person filming and one person firing the cannon so that later we can go back and look at the footage, do some wicked editing, determine how long it took for the bearing to strike the ground and how long it would travel.
And
Yeah,
we relied a little bit more on the paint stains on the floor than the measuring tape for that. Real
yeah,
scientific method there.
yeah, yeah.
Um, Speaking of,
Assumptions are kind of a big part of any experiment. It's just to make the information kind of dissectable so we can make sense of it, we can find our theories, etc., etc., etc. So we had to make some assumptions. We first assumed that air resistance wouldn't really have an effect, which, at least for the cannon part, is probably decently true, but it might have had more of an effect once the projectile was actually fired. We also had to assume that the cannon would function like a closed system and no energy would be lost to outside sources.
another assumption we made about the energy in the cannon was that each magnetic section would have the same amount of kinetic energy. So when they stacked on top of each other, they would produce an amplified effect of the kinetic energy. So each section would add the same amount of kinetic energy to the projectile, with the same amount of kinetic energy, the same amount of speed as well. One thing that's a little bit dangerous about assumptions, sometimes you get a little too broad with assumptions. Um, and so
Foreshadowing.
this is why our hypothesis may be making a couple incorrect assumptions. We'll get to that later.
Wow, I know what you're thinking, guys. That was really cool. Cool experiment, cool slides, I don't know. You know what's even cooler? You're right. Data. Here's our data. So we recorded 2 trials for each amount of magnets. So look at this, it's a bunch of numbers, you know. We took the average from the 2 trials just to have a more accurate reading of what it might be as
Part of the
far.
data looks kind of consistent with our hypothesis in that the distance to ink kind of by us the same amount, at least for the first three, or the first two. But then the last difference seems a little bit off, which we expected because of how projectile motion works. Um, we know that because there's only acceleration um, downwards, the time taken for the projectile to travel will not be affected by its horizontal motion. So all the projectiles should have traveled for around the same amount of time.
So here we've gone one step further using the equation that we decided we could use earlier. The average velocity equals change in distance over change in time. So plugging in our distance and time data points that we got from the last one, we find it's going from 2.6 to 3.8, 4.7, 5.0, which if you look at how much that's going up, it's actually going down quite a bit. You go from 1.2 to 0.9, 0.3. It seems like the amount that it's going up is getting shorter every time, which already it's not looking great for a hypothesis.
And not only that, it's not changing by the same number either, which is another part of our hypothesis.
Mm-hmm.
So clearly, our hypothesis has been disproved by the data.
Yeah.
But the data was not discouraging enough to completely turn us away. We figured that we might have missed something over the course of our experiment and our calculations. So we're wondering if anyone has any ideas as to what we might have missed. Ultimately, a lot of our problems were based on the hypothesis being not a very solid hypothesis. So we've mentioned previously that the kinetic energy is half of the mass times the velocity squared. So the kinetic energy is proportional to the speed squared. And squared numbers do not go up by the same number each time. Yet our hypothesis states that as the kinetic energy increases by the same time, or by the same number each time, the velocity should also increase by a same number, which is just not how those numbers work. So yes, we should have expected a systematic, just not by the same number each time. Another misconception was our assumption of how the cannon works. So I mentioned previously that our overly broad assumption might have gotten us in trouble, and it was that each magnetic slot should produce the same kinetic energy and they should stack perfectly. So like all of the kinetic energy, it was almost as if the kinetic energy from each slot would be independent of the kinetic energy from the other slots. So they would all perfectly add up, which is also not really how that works. And we'll explain that in a moment. Um, Despite our slightly messy hypothesis, the data speaks for itself when it comes to all the things that we can learn from it. So we were able to derive quite a few conclusions from the data about the cannon and the transfer energy in the cannon.
This transfer mostly has to do with something that we kind of ignored in our hypothesis, which is conservation of energy. So if you have your trigger bearing being placed into this cannon, it's going to accelerate towards the magnet, like we mentioned, and it's going to hit that magnet with a certain amount of momentum. Now, this momentum will be transferred into the next bearing, and this bearing is going to also accelerate towards the next magnet since it's propelled forward by the momentum. The thing is, when it's accelerating towards this magnet just before it starts, there's actually a lot of potential energy, which, is a big part of conservation of energy, potential energy. So here's where we would actually find the maximum amount of potential energy, because those magnets are what's causing this whole thing in the first place. And this is going to be very important. Um, this, as it accelerates towards the magnet, it speeds up and then it hits it, we're going to reach our maximum kinetic energy, which, if we remember conservation of energy, our maximum kinetic energy is going to equal our maximum potential energy.
The ball that is being hit by the trigger has a certain amount of stored potential energy, which once it starts going into motion, it will begin to convert into kinetic energy. And that energy will then be transferred to the final ball, which is shot out of the projectile or shot out of the cannon. And that ball has both the speed from the initial, from the trigger, and it has the speed from the second ball bearing, which had its potential energy transferred to kinetic energy. That kinetic energy, as we've said before, requires a certain amount of speed. So in order to transform all of that potential energy into kinetic energy, the ball would need to gain a certain amount of speed. And the trigger actually provides a fair amount of that speed, which means that the ball has to gain less speed on its own to convert all of its potential energy to kinetic energy to reach that maximum speed required to convert all the energy. So this means it adds less speed because a lot of its speed that it needed for the energy conversion um, is supplied by the previous slots. So as we increase the number of slots, the amount of energy or the amount of speed that is added on in each slot decreases because the speed it actually needs to convert its energy is being supplied by the previous slots. And that's why, as we saw in our data, with each magnetic slot that we added, the amount of extra or the amount of additional velocity that was supplied decreased because each time the balls had to move less quickly in order to compensate for the speed required to convert their energy.
Okay, but what does this mean for the possibility of sticking like 100 cannons together and breaking glass? Guys, we're really sorry.
It's
It's not gonna happen. It's not gonna happen. Ugh. Unless,
oh
unless,
wow.
unless, unless if you use stronger magnets, this would mean that the mechanical energy of the system would be higher, and the speed would have more room to increase. Because if you had stronger magnets, then that would be a higher maximum potential energy, higher maximum kinetic energy. It's going to speed up more. But our humble little cannon, it's not going to be achieving much more than what you've already seen. That, if you happen to have really strong magnets, probably don't do this still. But you could think about it, and it'll be really nice in your mind.
In
Conclusion.
conclusion, our hypothesis was disproved. And our hypothesis was a good lesson on how not to write a hypothesis. Um, so we observed, yes, a proportional increase between the amount of magnet sections, the energy produced, and so the velocity, but it was not in the way we thought it would be. Um, and so this led us to wonder how we could have made our experiment better. Perhaps we could have changed our hypothesis and changed the question we're trying to answer. Um, Maybe we could have made it a little bit more related to the experiment, related to what the results of the experiment were. Because you never know what's going to happen. You start out doing a projectile project, you wind up doing a whole bunch of stuff about conservation of energy. Um, Maybe we should have prepared a little bit better ahead of time. The
Yeah.
hypothesis was kind of a guess. Yeah. um, Maybe we should have thought a little bit more about it and tried to base it on a little bit more of a solid foundation. But we did learn something in the end. We did learn about how the cannon is limited in the velocity of the projectiles that it shoots, because at one point, if there are enough sections, then there will be no velocity that is added by the cannon by the new magnetic sections, because all of the previous sections are already supplying all velocity to convert the potential energy into kinetic energy, so there's no need for any new speed. So there would be no increase in the speed of the projectile; it would just stay the same.
We're gonna hand it over to our real life counterparts to ask you these questions. Hopefully, we're not running out of time. Enjoy.